Okay guys, in this experiment we will do the vibrational rotational energy for HCl hydrogen chloric gas, okay, for using the Ftir, okay. So because this is a HCl is a diatomic molecule, right? It's a very simple molecule. So this molecule will rotation and vibration at the same time. Now, of course, it's a translation, but the translation doesn't give any information about the molecular structure, right? Because translation, the whole molecules move as a single point. So we want to study the vibration and the rotation to find out the bond length from rotation and bond strength from the vibration. Now this is this experiment. This experiment is simple, but it contains a lot of information. Now because this is a diatomic molecule, so HCl, so it is a diatomic molecule, is very simple. So we can see both vibration and rotational energy level at the same time. If the molecule is complicated, you cannot see the rotational energy level because the rotational energy level is so fine, actually they smell out. For example, SO2, sulfur dioxide molecule, just one atom more, 3 atom molecule, you cannot see the rotational energy level. But this HCl and another one is DCl, deuterium chloride, we can see both. Now in this experiment, we will run both gas. Now first we will run the HCl, use the Ftir. Now this instrument is called Ftir. Ft means Fourier transfer. IR infrared spectroscopy, because your vibrational and rotational energy follow in the infrared energy, infrared range. So we can use this one to see how the molecular energy level, so quantized, okay? Now this Ft is called Fourier transfer because this one makes the measurement is much faster, much more precise, okay? So now this one is a very standard instrument in the research or in the teaching lab. Now this is a cell. We will put this one into your gas, okay? Now this is, we will feed the gas through here, and then of course another one will release the gas, right? So your HCl gas will feed inside. Now this two end actually is not glass. This is a KBr window, potassium chloride. The reason is regular glass, the IR cannot penetrate very well. So KBl can penetrate very well. Now this KBl, like a sodium chloride, very easy to absorb the moisture. So it will gradually dissolve. That's why you see that the surface is so blurred, because some of them are already dissolved. It's already dissolved. But we don't care this one because we treat this one as a background, okay? Then we measure the gas inside. We measure the background first. This background will include this KBr smear part and the oxygen inside. We measure the background first, then we fill some HCl gas there, we measure it again, okay? Then we will subtract the background. Then we will get the pure rotational vibrational spectroscopy of your HCl as well as the DCl. Now the instrument we will use is called Fdir instrument. So normally, so this is a switch, okay? So you turn on this switch, let the laser light up, okay? So now when you finish this one, you turn off this switch. We want to save the laser lifetime. But after you switch this one, the last light still on. It doesn't matter. That one is just indicate the power source. The power source is on, but it doesn't matter. The key point is we need to switch off this one, okay? So switch on when you do the experiment, okay? Then switch off. Now you switch on this one first, then turn on the computer, or you turn on the computer first, switch on this one, then. So you need to practice a little bit. Sometimes the time or the sequences matters. Okay, if the one doesn't work, you just switch to the other one. Now I already tuned up this one, so everything works fine. The first one we will measure the background, use FTIR. Now we slide this one in, open this one through here, compartment, okay. Now here is the stand here. Now this stand, you will slide this one into that stand. Now be careful which side you slide. So this side with arrow 452. This side slide in. The other side cannot slide in very well. So slide with the side with this arrow, and with the 452 number. So slide this side in, okay? So with arrow and 452 into your machine, okay? So slide, then cover it. Now, come here, we will use this program. This program is called Spectrum Manager, okay? So just double click this one, okay? It will pop out this program. Now this program has two parts. The top part is for you doing experiment. The bottom part for you to analyze the data, okay? Now when we do the experiment, we use the top one. The first one is your spectrum management. That is what we need, okay? You just double click it, okay? It says you are initializing your instrument. Try to collect this one. Then after they finish, okay, then they will pop up this window. You maximize this window. Now you can see this window, this S means your sample, B means your background. Now this is the parameter I wanted to show you, okay? Now first, this is IR. So the bottom one, the X, is called wave number, very often used in the FTIR. They don't use the frequency. They don't use the number. They use called wave number. What is the wave number? Wave number means so centimeter per centimeter. That means in 1 centimeter distance. For example, this is 1 centimeter, okay? This length, how many waves you can contain inside 1 centimeter is called one wave number. For example, we're starting from 4,000 to 400. One side is 4,000, okay? One side is 400. 4,000, that means in 1 centimeter you have 4,000 waves inside. Okay, 400 means 400 waves inside. So you can see the higher number, that means the frequency is higher, okay? So now frequency equals this wave number times the speed of light. But be careful, this one is in centimeter per centimeter, okay? You need to, time must be, unit must be consistent, okay? Now let me tell you what the parameters we use. Now this is a major parameter we use, okay? The key point is here, everything is here. The first one is called number of scans. We scan 16 times. So that means you do once, 16 times. We add them up to increase the signal noise ratio. Because the signal keep adding up, right? Noise is random, they will cancel. So we do the 16 times. Now the resolution is 1 per centimeter. That means 1 wave number per centimeter. This is 4,000, right? That is 1 wave number per centimeter. It's very precise. The range, we will scan from 4,000 to 400 wave number. Okay? The vertical is auto. Then we'll change this one to auto. Now the background, we just scan once. Okay? Now this is all the parameters you need to know. So actually you really don't worry about anything. So just know that it is from 4,000 to 400. Okay, we scan 16 times. The first one is we will put this one without any HCl gas, just air. Inside we try to measure its background. We just slide in again. Slide in this face, okay? So with the arrow and 452, slide this one in the stand, and then cover this one, okay? Now let's just click the B here. That means we will take the background first, okay? Now this is the background absorption of all the air inside, okay? So this one looks like nitrogen, this one is probably CO2, something like that, okay? So you will scan 16 times, you can see it's moving here. It's moving here, when it's finished, it will tell you, okay? So this is 9/16, 10/16, there is a small number here, so you can read this one. So when they finish, it will automatically stopped, okay? Okay, you can see now we take the background spectrums here, then later on this spectrum will subtract from your sample, okay? Then the later result will be spectrum completely from HCl gas. Okay guys, let's come here to fill the HCl gas inside of this one. As I said, this one is a KBR window, okay? It's not a regular glass, it's very easy to be moisturized. So that's why we store this one into the desiccator, okay? After you finish the lab, you need to open this one, then you use the air to blow out all your chemicals out, okay? Your HCl out, then close this one, then put this one back into this desiccator, okay? Now let's fill the gas. Now because we already measure all the air inside as a background, right? We just add a little bit extra HCl there. Now you don't want to open both of this one. If you open both of this one, you add the HCl, you blow out your air out, actually change your background. So you don't want to change the background. You close one, open another one, then fill the HCl gas on top of your air, right? Now HCl gas is quite corrosive, so you need to wear the gloves, okay? Now you put this one here, okay, on the table, and then you open one of these valves, and then you put this one, just put this one in, then open this valve, okay? Before you open this valve, to hold this one like this to test the HCl gas, okay? So you can feel the HCl gas come out. Yeah, then just put this one on the top. Then that's good enough. Close this one, then turn off this one, okay? Now you already feel the HCl gas inside on top of this air. So we already measured as a background. Now, guys, we already feel the hydrogen chloric HCl gas inside, right? We measured the background previously. Now let's measure the vibrant rotational spectroscopy of the HCl. Again, we slide this one in, okay? We slide this one in. Now cover this one. Now this time, go to the computer. We will click the sample, okay? Not the background, but click the sample. Now let's click the sample to see what it happens. Okay, so you can see this is the spectrum, okay? So it's HCl spectrum. Now this is a plateau, actually is vibrational. Now this individual one is rotational. So this is rotational on top of vibrational. Now in the handout, you read the handout, you can see we will miss the center part. This is because from rotational to the next bottom vibrant to next vibration, the rotational, J delta J equals 0 is forbidden. 1 to 1 is forbidden, 2 to 2 is forbidden. So that is why you're missing one peak, okay? It's very easy. You just finish this one. Now this is the spectrum you measured. Okay, now the next one is how we processing this spectrum. Okay, now we need to see the file. Okay, let's see. Okay, we click the file. Click the file, click the spectrum sync, okay? So you can see this is, so this is what we just saw that one, right? So you go to the file, click the file, then click the spec analysis send, the second one. So basically you send this spectrum from whatever your measurement to the analysis domain. So we can analyze it, okay? So now let's assume this one, we just finished this one, or we can do this one later again, okay? So then we minimize this one. So you can see we send it twice, there's a 2. So we don't need a 2, let's close this one. We just, so this is the spectrum in the analysis mode. Let's drag this one. We need to analyze this one, okay? Now first to analyze, we need to find, okay, what are the peaks we need, okay? What are the peaks we need? So we need to get rid of this noise. We need to get these peaks. Now you can see a lot of icons here. You just move one, it will tell you what you need, okay? The first one is the baseline correction. We don't need. You can search until the second one, smooth, we don't need, okay? You will see the peak height, we don't need. You will go to the peak finder, okay? So let's click the peak finder, okay? After you click the peak finder, it will ask you the threshold, because we need to set the threshold to get rid of this fine noise, okay? So let's see the upper limit. Upper limit is here, okay? So this one is for your upper limit. That means you cut this one above this one. So you can move this one. Okay, you can hold it here. Let's see. So you can see when you move this one up and down, this one changes, okay? How many peaks you include? Most of them is already enough, okay? Okay, so let's see what we do this one. Let's apply this one, okay? Now this is a peak you will get, okay? Now this one is the x-axis is too wide. We don't want to need this much of x-axis. So we can click the scale here. So we can change this one. You can see from 3200 to 2600 already cover most of them. So we can see from 3200 x-axis to the 2400. So 32 to 24, that will spread this one. Okay, so you can see this one, okay? Now here, be careful. If you look closely, you can see every one has 2 peaks. You can see this one and this one has 2 peaks. Why? This is because HCl, Cl has an isotope. Now Cl has an isotope. 2 isotopes are abundance very close. One is 45%, the other one is 55%. So Cl is chlorine. The chlorine, the atomic mass is 35, right? Another is 37. So one is a little bit abundant than the other one. So you have 2. But however, you just need one of them. You just compare either the bigger one or the small one. So that means your bigger one compare with the bigger one, compare with the bigger one, compare with the bigger one. So the bigger one is the heavy one, or chlorine 37 or 35. You can see this one, okay? This is high frequency end, right? The wave number corresponding frequency. The higher frequency, that means the vibrating faster. The vibrating faster, that means it must be lighter. So the atoms must be lighter. So this high peak actually is chlorine 35, okay? So the lower peak actually is chlorine 37, because the lower peak shifted to the slow frequency side, okay? So now we apply this one. So now how many peaks you have? You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So and this part is 22. 2. So that is more than enough you need. Now after we get this one, we will print this one. So you will select the peak, then you print this one, okay? So when you click the print, now very good. You click the print, then mark this peak, okay? Then mark the peak 1 corresponding position, that means frequency here. So peak 2 is a high peak, okay? So you're starting from peak 2. See, peak 2 is also higher peak. So peak 2 corresponding frequency here. You can see peak 2, 4, 6, 8, 10, all the even number corresponding high peaks, okay? So be careful. The first one, you forget this one. So because starting from the second one, that is high peak. So because you have so many data points, doesn't matter you drop 1 or 2, okay? You're starting from 2. 2, 4, 6, 8, 10. 2, 4, 6, 8, 10, etc. All the even number is what you want, okay? Because they compare with HCl35, okay? So this is the one, after you get this one, you print it, okay? Then you will print it here. So let me check this print. So anyhow, you will print it, you will get this one, okay? You will get exactly the same as this. Then you will use this data to do the calculations, okay? To do the calculation. This is this experiment. So after you finish HCl, you need to go to the other side to open both of them, then blow it with the air. Open. After you finish the HCl, okay, you open both of your valve, then go to use air to blow this one completely, okay? Blow it for 2 minutes, and then blow that completely. Then go there to feed another one DCl gas, which is exactly the same. Then come here to measure the DCl. Again, you just click the sample. It will measure the DCl. Then send it to data analysis. Then find the peak exactly the same as this, and then find the peak. Then print out this the peak number and the peak position. That is this experiment.